we are discussing double integration. In double integration, it is slightly different from single integration, because here you will have two symbols of integration. First, you will have a function of x and y. There will be two variables in this function, x and y. And most important thing in single integration, you are only focused on fx. If fx is simple, you can easily calculate its integration, antiderivative, because dx was just a symbol of integration here. You are focusing just on fx. But the unique thing in second integration, double integration, is that here you integrate along the x-axis in single integration by dividing it in infinite number of dx, small with dx. Whereas double integration is carried over an area, a region, not along the line. It is carried over a region. Here there are two things. Suppose this is f function of x and y. So let z is equal to f x and y. This is coordinate system x, z and y. X and y will lie on this. All function points will lie on xy plane. But and we have used z is equal to fxy. So for every value of f, x and y, there will be a value of z. So point x comma y comma z, we will get a point x comma y comma z. X comma y will be point on x and y axis. In xy plane, you have a point x comma y. You put this point in this function of x and y. You will find third coordinate z. By finding z, you will find point x, y, z. It will be in space, in volumetric form. xy is in xy plane and xyz point is somewhere in space between x, y, z. So here you write it like this. Now, as we have said that this double integration is carried over an area, not along the line. So what about this area? Here we just define simply fx is equal to let x square plus 1. That is enough. X square 1 integrated. Here only we cannot like this. Here we use dx dy. What is dx dy? Dx dy is a small rectangle, small square rectangle. It's along the z, along y, its length is, its dimension is dy, and along z, along x axis, its dimension is dx. So dx into dy is area of this small element. Dx dy is nothing but area of small element. Dy is along dy y direction, small length y direction, and dx is small length along x direction, and this dx into dy, you can assume it dx into dy, so this will be dA. Dx in dy you can write as dA. This is very small area. So now this small area, let there is a region bounded by this shape. So you want to calculate, so there will be a function for this to define this shape also, this area also. So here you write it like this, A, along the region A. So this dx dy, in this you find just a small element dx dy, and you have to sweep all this area by vertically moving this small element and moving along the y-axis and moving along the x-axis this small element. You have to sweep whole this region. This sweeping will define its limits. So this area has its own curve function. So here you will have two functions. First function is fxy, and second function which will define this area, and then you will define the limits a to b, c to d, something like that, based on this range of this small element within this area. Within this area, this element has to cover whole area, which will define its range. Let us take an example. So you see, if fxy, fx comma y is equal to 1, the most simple function, then it can be written as 1 dx dy. This is 1 dx dy. So here dx into dy is a small area, and when you multiply this small area with 1, what you get? A volume. Volume of small, very thin cube with its base at dx dy and height as 1. So this is the sum. Just earlier we have seen it is fx into dx. It is the area of general triangle. Similarly here it is the volume. It is the volume with area which is obtained by multiplying this area and value of function at a general point. So it will, this whole expression will give a volume. Though it is a double integration and people perceive it like this, it will give an area, but it is actually giving us a volume. Let us take an example. So now we will solve question of double integration. How the double integration is applied in physics. So we will take very simple problem to solve. Let there is a region, as we have discussed in double integration, there are two functions, original function as well as a function which defines region. So region is defined as, there is a region defined as x is equal to less than 1 and greater than minus 1, and y is equal to less than or equal to x square and greater than or equal to minus 1. This is a region over which we have to integrate. This is a region, and there is a function. So just we will draw this region first. We know y equal to x square is this function, parabola y equal to minus x square is this parabola, x equal to 1 and x equal to minus 1. So this region y is less than x square. At this, over this curve y will be equal to x square, and less than x square means all points below this curve. Similarly y is greater than minus x square. So this is y is equal to x square, and this is y is equal to minus x square. Greater than minus x square means points above this curve. So this region is this. Satisfying this equation, the region will be shown by this shaded region. X is equal to 1, x is equal to minus 1. There is a function, the value, suppose this is the area, even though this area looks awkward, but just we will assume this is the area, cross section area, and value of flow perpendicular this cross section is given by a function x comma y is equal to power 4 minus 2. At point, this is x-axis and this is y-axis. So at point x comma y, you can say anywhere x comma y. The flow of water is given by this equation. Flow of water is given by this equation. So at this, during this region, water has different magnitude of flow. So we have to calculate, sorry, this is the velocity. The velocity of fluid at point x comma y is given by this equation. That it is in meter per second. So we have to find flow through this shaded region. Flow through this shaded region. Here we will use double integration to solve the problem. So let us take a small element dx and dy along x-axis length dx, along y-axis length dy. So area of this small element is dx dy. And at this point, at this area, let the point is x comma y. At this point x comma y, velocity is this. Even though velocity is changing at a point, so we will assume that at dx and dy region, velocity is constant. So dq, flow is equal to area into velocity, is equal to area is dx dy and velocity is x to the power 4 minus 2. So this is flow through this small area. As we have assumed velocity at this point x comma y constant in this small area dx into dy. So this is just approximately equal to, I will say approximately, not exactly, because velocity is changing. Velocity is changing even during this small region also, no matter how small this is, because velocity is fixed at a point, even at a point x comma y. In this region also velocity will change. So flow will not exactly equal to this. It will be approximately equal to this, because as the area will be smaller and smaller, we will get more accurate flow. So small flow through this area is approximately equal to this. Now to find flow Q, as we know dq, integrate both sides over this region R. As we use the sign integration, this approximate sign converts into exact equal sign by the definition of integration itself. This operator takes care this operation, because when we will integrate, the Riemann series will be made, and this Riemann series will make this dx into dy both tending to 0. Dx is delta x is tending to 0 and delta y is tending to 0. that is the flow will be exactly equal to expression given by this double integration. This double integration operator takes care by Riemann series. Limiting value of addition of infinite series will be achieved by this double integration. So this is x to the power 4 minus 2y dx dy. Now define the limits for x. It is this small element will sweep through this shaded area. It will sweep from -1 to +1 for x in x direction. In y direction, it will come to y equal to x square and y equal to minus x square. It will reciprocate between these two curves, y equal to x square, y equal to minus x square. So limit of in y direction will be minus x square to plus x square. So this is total flow. Again, you remember this exact sign of equality. Here it was approximation, because this was approximating the flow constant over this small element. So it was approximately equal to, whereas when we use integration, it will be exactly equal. So now integrate it. Now we will integrate this. First of all, with respect to y, limit -1 to +1. X to the power 4y minus 2y square by 2 minus x square dx. We have integrated with respect to y, assuming x as constant. X as constant as Fibonacci series, Fibonacci theorem. We have explained that we can carry out the integration in any order. First, you can integrate with respect to y, and second with respect to dx, x, or you can first integrate with respect to x and then y. That is Fibonacci theorem. The order of integration doesn't matter. So here, this is equal to -1 to +1. This will cancel. This is equal to minus x to the power 6 minus power 6 minus x power 4, put the value x square, minus x power 4 into minus x square, that is minus x power 4 minus 6 minus y square, put minus x square y square. So it will be -1 to +1, x to the power 6 minus x to the power 4 plus x to the power 6, and this is positive, negative, positive x dx. Now it is integration -1 to +1. These will cancel. X to the power 6 dx. So we have just committed a mistake. So these both will add, will come 2x power 6, and this is 2x power 7 by 7 minus 1 plus 1, which is equal to 2 1 by 7 minus 1 by 7. This is equal to 2 into 2 by 7, 4 by 7. So Q is, we have calculated Q is 4 by 7 meter cube per second. If this area is given in terms of meter square and velocity is given in terms of, this velocity is given in terms of meter per second. Velocity given by the function is in terms of meter per second, and area is given in terms of meter square. Then this flow through this shaded region will be 4 by 7 meter per second square. So this is a method, this is the way we use double integration in physical problems. So double integration, as we have discussed, there is a equation of area and there is equation of function. Here equation of area is given by, here we have found equation of area as well as equation of function. Equation of area was x is less than 1 greater than minus 1 and y is less than x square and greater than minus x square. This was equation of area, region, and equation of function fxy was x to the power 4 minus 2y. So we had two functions in double integration. This function was giving velocity at point x comma y, and this function was representing a region through which water is flowing. So by double integration we have found flow through this region. This function gives velocity in terms of meter per second, is meter per second left, and this area is represented in terms of meter square. So we found flow in terms of meter cube per second. Another important thing, actually sometimes you will feel the questions are very difficult for double integration and triple integration with normal Cartesian coordinate x and y form. You have to change them in polar coordinates. So we will just understand what is polar coordinate and how to change them. This change of coordinate from x, y coordinate Cartesian system to polar, cylindrical coordinate, spherical coordinate make problems of double integration and triple integration very easy. Otherwise you will have very cumbersome exercise to find double and triple integration. And when you convert them in cylindrical and spherical coordinate system, based on the situation, based on the type of shape given of area or volume, this problem simplifies greatly. So you will just understand what is normal coordinate system C. This is Cartesian coordinate system, Z, Y, X, and a point P is coordinates are given by x, y, z. There is another system called cylindrical coordinate system, which is a part of polar coordinates. In polar coordinates, point P is written as r theta z. R theta z. And what are these? This is y axis, this is z axis, and this is x axis. r theta z. So same point. What is r? R is distance between origin and P. Sorry, it is not distance between origin and P. See here, this is x and y. So r is distance in xy plane. XY plane, distance of projection of this actual point in space in xy plane, xy, and theta is angle with x-axis. So here we write x is equal to, for point P, x, y, z, x is equal to r cos theta, y is equal to r sin theta, and z is third coordinate. So to find r, this point is P, same point was there, but it was represented at x, y, z. Now it is represented at r, theta, z. Z is same. This is actually cylindrical polar coordinates. Okay. So r is, make the projection of this point on xy plane, and this cuts the xy plane at this point P dash. Length OP dash is r. Theta is angle between OP and x-axis. So x is r cos theta. R cos theta is component in x direction. Y is r sin theta in y direction, and z is z. So it is written as r theta z. And third is cylindrical coordinate system. Here coordinates are represented as rho, theta, phi. Rho is, this is the same point P, this same point, but representation is different. Rho is this is y, this is z, and this is x. Rho is distance between O, origin, and P. Straight this distance between OP. Here R was distance between projection of P and O. Rho is this distance. Theta is same. Projection of this in xy plane, P dash. Again you can write R, and angle between x and OP dash is theta. Phi is angle between Z and OP. This is phi. So here in this is called spherical coordinate system. Spherical coordinate system. Here you can write x is equal to rho sin phi. This is rho sin phi. And x is equal to x component of this into cos theta. X is equal to rho sin phi into cos theta. Similarly, y is equal to rho sin phi. This is r. Y is equal to rho sin phi into sin theta in y direction. And third is phi. Third coordinate is phi. And rho is equal to under root x square plus y square plus z square. So this is the relation in normal Cartesian cylindrical polar coordinate system. Again we will write relation between dx dy and dx dy dz in different Cartesian coordinates. Suppose in Cartesian coordinate system y, z, x. So we write dA is equal to dx into dy, dx dy in Cartesian system, normal Cartesian system. In xy plane there is small area dx into dy. how we denote this dA in cylindrical coordinate system? In cylindrical coordinate system, here we have assumed it a rectangle. Here we will assume this dA is equal to a arc in the form of arc. And this is R. Along the radius, it's is dr. This angle is theta. Point was R, theta, z, and it was its projection P. So the area dA of this arc, area of arc dA is equal to radius into, suppose this is d theta, radius into d theta into, let is this arc you assume a small rectangle because d theta is very small, and dr, this is dr, along the radius, small increment in radius, in radial distance, dr. So this is a rectangle, small, actually this is arc shape, but dA, this is very, shape is very small, so we can approximate it to a rectangle with this length is dr and arc length is r into d theta. So area dA of this arc is r d theta into dr. dA is this. So in cylindrical system, we will write dV is equal to dA into dz is equal to r d theta dr dz. This is how we write dV in polar coordinates. In cylindrical form, in Cartesian form, dV will be written as dx dy dz. We will assume a small cuboid shape with dimension dx, dy and dz. So this is the volume, small volume element, and in cylindrical form, small volume element is given by this. Similarly, we will find dV in spherical form. In spherical form, these point coordinates are written as rho, theta, phi. So here you find a small volume like this. Here it is rho, distance is rho. This is small dV volume. So this is z, y axis, x axis. Just projection of this, find this arc. This is the volumetric part of spherical shape, and this will be the arc, and the length of this arc is r into d theta. R into d theta, as we have found it earlier, r into d theta, r into d theta. Similarly, so one side, it will also act as a small cuboid, but its shape is spherical, but for as it is very small, we are assuming it very small, so it will act as a small cuboid. We want to find all three sides of this cuboid to find the dV in spherical form. R d theta is one side. Similarly, this angle is phi from z axis. So this length is rho d phi. this length is rho d phi, and third length along this radius, along the radius is d rho. So we have found all three sides of this small cuboid in the shape of arc. So this r into d theta is, r is what? R is rho sin phi. So this r d theta will be rho sin phi into d theta. Now multiply all these sides of this cuboid. Actually it is not cuboid, it is spherical in nature, but as it is very small, we are assuming it as a cuboid. And finding its all three sides, multiply these all three sides, find the volume. So one side was r d theta, which is r equal to rho sin phi d theta, and second side is rho theta, rho d phi, rho d phi, and third side is radial distance. This is rho radially dr, d rho. So this is volume dv. This will be rho square, rho square sin phi d theta d phi d rho. This is dv in spherical form. So we will just write all these expressions at one place. In Cartesian form, dv is equal to dx, dy, dz. In cylindrical form, dv is equal to r d theta, r d theta, d r and dz, r d theta dz. It is cylindrical coordinate system, and in spherical form, dv is equal to rho square sin phi d theta d psi d rho. This is spherical form. In all form, we denote dv in different ways. So you just remember it. We will use it in future. Another small discussion we will have to how to convert these all polar to cylinder, cylindrical to Cartesian coordinate system. We will go through an example actually. Let this is cylindrical coordinate 3 pi by 3 minus 4. We know cylindrical coordinates are written as r, theta, z. Convert this coordinate in Cartesian coordinate system. So as formula discussed earlier, x is equal to r cos theta is equal to r is 3, cos theta cos 60 degree 1 by 2 is equal to 3 by 2. Y is equal to r sin phi, r sin theta is equal to 3 sin 60 degrees root 3 by 3 root 3 by 2, and z is equal to, as it is given, minus 4. So Cartesian coordinate is x, y, z is 3 by 2 minus 3 by 2, 3 root 3 by 2 and minus 4. This is the Cartesian coordinate system. Similarly, Another small example, we will convert from Cartesian coordinate system to cylindrical coordinate system. Cartesian coordinates are given -2, 2, 3. So these are x, y, z. Cylindrical coordinate we know r is equal to x is equal to r cos theta. We can say r is equal to under root x square plus y square is equal to xy under root 4 plus 4 is equal to under root 8 2 root 2. Or tan theta is equal to y by x. Y by x. 2 by minus is equal to -1. This is 3 pi by 4. And z is equal to, as it is written, 3. So Cartesian coordinate system, polar coordinates will be r, theta, r is 2 root 2, theta is 3 pi by 4, z is 3. So Cartesian coordinate system has been converted into cylindrical coordinate system. Another small example, Cartesian to spherical. We will convert Cartesian to spherical coordinate. In Cartesian form it is given 2 root 3, 6, minus 4. This is x, this is y, this is z. We will convert it in spherical form. Spherical we know that rho is equal to under root x square plus y square plus z square is equal to under root 12 plus 36 plus 16. This is 8. Similarly, tan theta is equal to y by x is equal to 6 by 2 root 3 is equal to under root 3. This implies theta is equal to pi by 3. And third is psi. We know rho z is equal to rho cos psi. Cos psi is equal to z by rho. Z is -4. Rho is 8. This is -1 by 2. This is 2 pi by 3. Cylindrical coordinate system in the form of rho, theta, psi will be 8 theta psi 2 pi by 3. This is the way we convert these coordinates from one form to other, from Cartesian coordinate system to spherical coordinate system, etc. We will just have third integration example. Third integration, let a function is fx comma y comma z. In second integration we had fx comma y. In first integration we had fx. Here we had fx comma y comma z. The strange thing about this function is that this function cannot be visualized in any coordinate system. Unlike fx comma y, we were having z is equal to fx comma y. So in xy plane we took a point xy, found the z, putting the point xy in this function and made the point x comma y comma z. So those all points will make the shape fx comma y. But here it will need 4 dimensions actually. 4 dimensions. It cannot be written in xyz coordinate system, because if you assume that some fourth dimension let G is equal to fx comma y comma z, then there is a point x comma y comma z, and that point you will put in this function, you will find G. So where you will represent fourth dimension. So this function cannot be visualized, unlike function of xy, which can be visualized in xyz coordinate. So here also we define triple integration as we have to triple integrate it f x comma y comma z, and in double integration we were having a area dx dy, region, given region. In triple integration we denote it like this: v dx dy dz. This is a small volume area, volumetric area. So triple integration, there is a function, there is small volume, very small volume, this one length will be dx, one will be dy, and one will be dz. So this will be a cuboid with dimension dx into dy into dz, and this will give the area of that small elemental cuboid, that is called dv is equal to dx dy dz. Similar to second integration, double integration, which is carried out over a region, this is carried out over a volume. Here you will have function fx, and you will have a function of a volumetric shape, like a sphere, paraboloid, hyperboloid, something like that, hemisphere, any shape, volumetric shape. So in that volumetric shape, suppose this is a sphere. This is a sphere. X square plus y square plus z square a square. This is the sphere. So you have to integrate this function in this region. There are, similar to second double integration, there was integration of a function along a region. So there were two things: one, function itself, and second, function of region, equation of region. Similarly here you will have two things: function itself fx comma y comma z, and equation of volume. So what does it mean actually? So similarly, this is a function, and at small volume this function is multiplied. So now we will discuss the problem of triple integration. We will take very simple examples of triple integration and how we use this triple integration in physical problems. So similar to double integration, there was a function which was representing region, there was a function which was representing flow. In double integration also, there will be a region which will represent volume. In triple integration problems, there will be a region which will represent volume, and there will be a function of certain physical quantity. So let us see some application of triple integration in physical problem. Let there is function fx we have taken very simple problem just for explaining the concept. There is function given by at certain point x comma y. Sorry, this is function x y z. At point x comma y comma z, this function is represented by this expression, and this function gives the velocity density. Let us assume that this function gives the density in region at point x comma y, that is in this function is giving density. Okay, so let take x y z. Kilogram per meter is meter cube. Density at a point given by this function at x comma y comma z in kg per meter cube. There is a region, hemispherical region in x, y, z. So let us make this graph simple. That there is hemisphere. And equation of volume of this hemisphere is given as z is greater than 0 less than under root a square minus x square minus y square. So this is a hemisphere of radius a. From this equation, this is radius a. More than 0, let this is z axis. Well, this hemisphere only exists in positive z direction, and less than a square minus x square minus y square. This is equation of sphere. Equation of sphere is x square plus y square plus z square is equal to a square. From here you can write z square is equal to a square minus x square minus y square, and z is equal to plus minus under root a square minus x square minus y square. So only plus sign is given, that means they are considering only upper half volume, that is positive side volume of hemisphere. So that only plus sign they have mentioned. So there is volumetric region given by this equation, which is equation of sphere. As it is more than only above greater than 0, that means it is equation of hemisphere, because full equation of sphere is x square plus y square plus z square equal to x. So you have to find mass of this hemisphere. We have to find mass of this hemisphere. So let a small element, assume a small element of dx, dy and dz dimension in x, y, z, small cuboid. So volume of this cuboid is dv is equal to dx, dy, dz. Density is given at a point. So during this small volume, density will change, but this volume is very small. So we can say the mass of this small volume will be approximately equal to function f x y z, density function, into d. So generally you should remember, in physics we don't use this approximate sign, we just write dm is equal to f x y z into d dot dv. We don't use this approximate sign, but I have just used it to classify how integration, when we use integration sign, that integration sign really changes this approximation into exact calculation. That's why I am using it. Otherwise, in normal writing in exam and practice, you need not to write this approximate sign. this I have just tried to clear the concept, because fx y z is a density function at a point, and this dv will, no matter how small this volume is, it will contain infinite number of points, and those points will have different density. So this mass will never be equal to this, because the density function is not constant over the region dv. Density is changing, hence it is approximately equal. And when you will use integrate sign, then approximation will convert into exact equality sign, because the operator integration takes care by its definition, the Riemann series, due to Riemann series, it is infinite sum of infinitely small elements which volume is tending to 0. So you just write it, 3x square plus y square plus z square dx dy dz. This is dm, mass of this small element. So triple integrate both sides. So this approximate sign will convert into exact sign over the volumetric region. Over the volumetric region, now it has converted to exact sign. Now we have to integrate this to find actual mass of this hemisphere. We have to integrate. Let's take 3 outside of this integration sign. X square plus y square plus z square dx dy dz, and the range of dx dy dz will change based on motion of this small element, will sweep the whole area by this small element. But this limit which you will get will be slightly complicated, because for x-axis it will be from 0 to a, but for y and z you will find limit in terms of under root a square minus x square minus y square, and the integration problem will be difficult to carry out. So we will convert this integration in terms of polar coordinates of spherical polar coordinates. Spherical form, this coordinate we will convert in spherical form, and after converting in spherical form, it can be, these limits will be simplified and whole expression will also be simplified. So just recall what we have mentioned during conversion from Cartesian to polar coordinate. Rho is equal to under root x square plus y square plus z square, and dv is equal to dx dy dz was equal to rho square sin psi d rho d theta and d psi. So this conversion we have taken directly from Cartesian to spherical coordinate system. So after this conversion, we will write this expression as x square plus y square plus z square is rho square. So this is rho square into dx dy dz. Dx dy dz is dv. This is this. So this is rho square sin psi d rho d theta d psi. Now we will fix the limit of these rho, theta and psi. Just recall conversion from Cartesian to spherical coordinate. Rho is changed from 0 to radius. 0 to radius is A. This volume is given by this A square minus x square minus y square. So this sphere is having radius A. And what is R? This is Z. This is Y. And this was X. So what is R? R is the projection of this point on xy coordinate and making angle theta from x-axis. So R will change when this small volume will sweep the area, then R will change from 0 to 2 pi. Sorry, theta will change from 0 to 2 pi. Theta is this angle with x-axis from projection line of this point. So the theta will change 0 to 2 pi to cover whole hemispherical circumference. Similarly, psi. Psi is the angle of point with z-axis. This is psi. This will change from 0 to pi by 2. So this is total mass. This is total mass. Now we will integrate it is equal to 3. From Fibonacci's theorem, we have mentioned that we can integrate in any order. Double and triple integration can be integrated in any order. So this is 0 to pi by 2, 0 to 2 pi, and rho is 0 to a. So this is rho to power 4, that is rho to power 5 by 5, 0 to a d theta d psi. So this can be written as 3 by 5 into a to power 4 a to power 5 integration 0 to pi by 2. Now we will, and sorry, this sin psi is also there. Sin psi with theta, with respect to theta, that is theta 0 to 2 pi sin psi d psi. So this can be written as this 2 pi will come outside. So this is 6 pi a power 5 by 5 integration 0 to pi by 2 sin psi d psi. So what is this? 6 pi a to power 5 by 5 sin psi is minus cos psi 0 to pi by 2. This is 6 pi a power 5 by 5 cos pi by 2 0 minus minus 1. So this is 6 pi a power 5 by, that is kilogram. This total mass 6 pi a power 5 by 5 kilogram. So this is the way we use triple integration, and we use conversion techniques from Cartesian coordinate system to spherical coordinate system to simplify the problem. We could calculate it from Cartesian coordinate also, but that calculation was quite cumbersome. Here the whole process became easy by converting this Cartesian into spherical coordinate system. Similarly, we will take another problem of triple integration. Triple integration. Let there is cylinder. There is cylinder. This is z equal to 0 and its height is z equal to 2. And the volume is represented, volume of this cylinder is represented by z is greater than 0, z is less than 2, and z is x square minus y square is less than or equal to 4 and greater than or equal to 1. This is the way the volume of this cylinder is represented. This is a hollow cylinder. So the volume of the cylinder is represented by this. So that means the z is changing from 0 to 2. That means height of cylinder is 2. And this is equation of circle. X square minus y square equal to 1 inner circle. X square minus y square equal to 2 square outer circle. So the radius of inner circle is 1 and radius of outer circle is 2. So this is a hollow cylinder with inner radius 1 and outer radius 2. Height z. Similarly, we have a function. In triple integration, we have a function of volume and we have a function itself. So there is a function f x y z is equal to 2z. Very simple function. Similarly, this 2z, just like a spherical problem we have carried out earlier, assume that at point x comma y comma z, the density of this sphere is given by this function kg per meter cube in meter cube, and volume is given in terms of meter cube. So find the mass. Similarly, assume a small area, small volume dV. So we will not discuss all those things again which we have discussed in spherical problem. dV is equal to dx dy dz here. A small element, cuboid element with dx dy dz dimension in x y z, dx dy dz at point x comma y comma z. At this point density is 2z, so dm is equal to mass into density into volume. So density is 2z. So this will also be approximate because this density is unique at a particular point and this whole area will have number of points, infinite points. So this density cannot be, mass cannot be achieved directly by multiplying volume into density because density is varying in this region also, dV, region dV also. This will be approximate, but since now we will use equality sign as usual it is used. It is understood that it is approximately equal to, but in general we use this exact equality sign. So dm is equal to density into volume, dx dy dz. So mass is equal to, carry out triple integration both sides, dm over the volume of this hollow cylinder is equal to triple integration 2z dx dy dz. Now this problem, we will simplify this problem by converting Cartesian coordinate system into cylindrical coordinate system. Cylindrical coordinate system, this problem will be extensive, greatly simplified. So just recall, in cylindrical coordinate system, point x comma y comma z are represented as r theta z, where r is equal to under root x square plus y square. R is equal to under root x square plus y square. So and theta tan theta is equal to y by x, and dv is equal to dx dy dz is equal to r d theta dr dz. So these were the conversion from Cartesian coordinate system to cylindrical coordinate system. So we can write this expression of dm as triple integration, that to take 2 outside, z dx dy dz is r d theta dr dz, r d theta dr dz. Now put the limits of all these d theta in xy direction, angle from x axis. So this volume has to sweep this small element volume has to sweep all this volume of hollow cylinder. So this small volume will travel from z equal to 0 to z equal to 2, z equal to 0 to z equal to 2. That is the limit of z. R, this dr. dr is inner radius and outer radius. This is 1 to 2. d theta, angle from x-axis. So for all points in this cylinder, this angle will change from 0 to 2 pi. So this we can write as, from Leibniz theorem we can integrate in any order, 0 to 2, 1 to 2, 0 to 2 pi for theta. So this is theta 0 to 2 pi z r d theta dz. So this is 2 pi 4 pi integration 0 to 2, 1 to 2, z into r d theta dr and dz. This is dr. This can be written as 4 pi 0 to 2. We will, with respect to r, z r square by 2, 1 to 2 dz. So this can be written as 4 pi 0 to 2. This is 4 by 2 minus 1 by 2 into z dz. This is 3 by 2. 3 by 2, we will take it outside. So this is 6 pi and 0 to 2 z dz. This is 6 pi z square by 2, 0 to 2. This is 6 pi 4 by 2, 12 pi. So total mass of this hollow cylinder is 12 pi kilogram. This is the way we use triple integration problems. So by using cylindrical coordinate system from Cartesian coordinate system, we made the problem easy to understand, and how the triple integration expressions are converted from Cartesian to cylindrical coordinate system to make them simple, and how the concept of physics are also applied to use triple integration method. Here we have found mass, which is very simple problem. To just explain how the concept is used, concept of triple integration is used in physical problems.